This model was made as an exercise at behavioral cloning and is based on an nVidia model presented in Udemy Applied Deep Learning, the complete self-driving car course, with some improvements over it. Let me start with talking about the simulator with which it was possible. It is open source Udacity's self-driving car simulator and can be downloaded from the GitHub. If you're interested, just Google it. Also, I will paste a link in the description. Let me run it. Here you can set the resolution and graphics quality. Certainly better quality means it will look prettier, but in the same time there will be much more details which are redundant for our model. In the original course it was advised to run it on fastest quality, but I thought that it will be interesting to increase a challenge. Therefore I made it with good settings on 800 by 600 resolution. Let me run it. One second please. And okay, the simulator has two modes, training and autonomous. Training mode allows to collect training data by driving the car manually, while in the autonomous mode the car will be driven by the trained neural network. During driving, the simulator collects telemetry in form of 3 pictures, one from the center, one from the left and one from the right of the hood, something about 14 times per second. For each picture, it is provided the steering angle, negative for the left turns, positive for the right turns, speed, throttle and brake levels. The simulator has some limitations such as no lap time or off track and wrong direction indicators. That's why it is hardly applicable for the artificial intelligence tasks and can be easily used for behavioral cloning only. Okay, now about the files. There are testing script drive.py and training script carracing.py. Let me start with the training script. I will not cover it in full details, but there are some important moments. The first of them is the distribution of the steering angles, because it can be biased with steering straight. Let me show it. Here you can see the central column is when we are steering straight. Let us remove the sum of the pictures. A few seconds please. And here it is, our uniformed data set. Also, to make the dataset more variative, few randomly applied augmentations could be used. Images can be randomly zoomed. Randomly panned. Randomly brightened. And also darkened and randomly flipped. Please note then when the image is flipped, the steering angle should be flipped as well. Next, the image should be pre-processed. At first we are removing the irrelevant parts of it, such as the hood of the car and the sky. Also, the color scheme should be changed to YUV, which is more efficient at a nVidia model. Gaussian blur should be applied to make the image smoother with less noise. The images are fed to the neural network by the generator, which can generate batches of data parallel to the training of the network. The model itself is nVidia, which consists of few convolutional layers, which will make feature engineering by creating a set of filters, which will be increasingly abstract from layer to layer. After that, the data should be flattened and fed to the series of fully connected layers. Activation function is ReLU. That's why, because ReLU, in ReLU, some gradients can be fragile during training and can die. It can cause a weight update, which will make it never activate at any data point again. Simply saying, ReLU could result in dead neurons, and ReLU prevents it. I have upgraded the model by adding callbacks to it. The first is learning rate reduction on the plateau, which will reduce the learning rate if validation loss will not decrease for 2 epochs. The second is early stop. Okay, early stop will stop learning if it will be no progress for 10 epochs and restore the best rates. I believe it allowed the car to travel at full speed at 30 miles per hour, while in the course it was able to do it only at 10 miles per hour. Now to the driving script. The simulator works as a server while driving acts as a client. Flask web app framework allows to do it. Let me run the script, the driving script. Change the simulator to autonomous mode. And here it is. Let's go to the script. Here we set the speed limit. Image preprocessing is the same as in training. Telemetry is the main function. We get the speed and the image, preprocess it, and fit it to the model to get the steering angle. I've made some changes to the code from Udacity's course. Actually, the formula when the throttle is equal to 1 minus speed divided by speed limit doesn't provide us with the accurate speed. Thus, I cut a few corners here, but the system, when we go full throttle when below max speed and completely cut the throttle when over or equal to, actually works. Let me change it. Actually, let us change the graphics quality and look if the model will work at better quality graphics. And here it is. We are going near the speed limits and everything works fine. Let us look at the driving. At the same time, I would say about this data. To the left is our steering angle. Please note that, as I said before, negative is turning left, positive is turning right, 0 is turning straight. Here it's a throttle, and here is our speed. There is some wobbling, but it looks the car can handle driving itself. Okay, I will leave the simulator and test if the car could complete the whole lap. And that's it. It looks like the car was able to complete the whole lap successfully. If you've got any questions, please leave them in the comments.